How can amplifier design overcome transistor gain variations? Imagine building a sound system that sounds perfect every time, no matter the tiny differences in the parts inside. That's what good amplifier design aims for when dealing with transistor gain variations. Transistor gain, also called beta or HFE, can change a lot from one device to another. This makes designing reliable amplifiers tricky because the gain might not stay consistent. But engineers have clever ways to fix this problem and keep the performance steady. One of the most common methods is negative feedback. Think of it like a thermostat that keeps your room at the right temperature. In an amplifier, a part of the output is fed back to the input in a way that opposes the original signal. This feedback makes the overall gain depend more on resistors and capacitors, which are manufactured with tight tolerances. So, even if the transistor's gain varies, the amplifier still delivers a stable output. For example, in a common emitter amplifier with a resistor in the emitter path, the voltage gain depends mainly on the ratio of the collector resistor to the emitter resistor. This approach is used in both discrete circuits and integrated circuits. Another trick is using differential amplifiers and current mirrors. Differential amplifiers use to match transistors to amplify the difference between two signals. If the gain of each transistor varies, they tend to change together, so the difference stays the same. This cancels out the effect of gain variations. Current mirrors copy a reference current to other parts of the circuit, and because they use matched transistors, the current remains steady even if individual transistor gains change. When designing integrated circuits, placing matched transistors close together helps ensure they behave similarly, reducing the impact of gain differences. Designers also use compensation techniques to keep amplifiers stable across different conditions. Miller compensation involves adding a capacitor around a high gain stage to control how the amplifier responds at different frequencies. This prevents oscillations and keeps the amplifier stable, even if the transistor gains drift due to temperature or aging. These networks help maintain consistent performance over time and varying environments. In real-world applications, engineers often combine these methods. An operational amplifier, for example, might use negative feedback to set the gain, differential input stages to reject common variations, and internal compensation to keep everything stable. These strategies make sure the amplifier performs predictably whether it's used in audio equipment, sensor systems, or embedded electronics. Remember, the key is that the gain of a transistor can vary, but with smart circuit design, that variation becomes less important. By relying on passive components, matched transistors, and compensation networks, engineers create amplifiers that work reliably every time, no matter the tiny differences inside the transistors. This approach is fundamental to building high-quality, dependable analog electronics used in countless devices around us.